These are images of the beautiful scenery here in Prince Edward Island, showcasing its famous red soil. But did you know that the red color actually comes from rust? PEI soil has a high concentration of iron oxide, which is rust. And while we like it in our scenery, we don't like it on our cars. But how does it get there? And how can we prevent it? That will require us to learn about redox reactions. So today we are talking about redox processes or redox reactions. Redox coming from the words reduction and oxidation, right? So reduction and oxidation, we'll talk about those, but they happen together. They happen at the same time. You can't have one without the other. When one chemical species is reduced, the other one is oxidized. But what does any of that mean? Well, fundamentally, redox processes are all about essentially electron transfers. In other words, we are thinking about chemical processes where electrons are essentially donated from one species to another. So in the products, all of our atoms have a certain number of electrons, but in the reactants, all of our reactants have a certain number of electrons, but in the products, some of them have different numbers of electrons. So the electron numbers change. Now that isn't true of all chemical reactions. You can break a chemical bond and keep all the atoms with the same number of electrons they had. They can take them with them and go form other bonds. If that happens, then you don't have a redox process. A redox reaction happens when electrons are stripped away from one species and given to another species, right? So they're pretty prevalent, but it's all about electron transfer. And so that's what we need to talk about. We need to keep track of electrons. We need to keep track of where they are. And the way we do that is by something called the oxidation state or the oxidation number. We need to know what is the oxidation state of each and every atom in a particular chemical species. So let's start with that. First of all, an oxidation number is essentially the charge that we would assign an atom if we took its electrons and distributed them as though the bond was ionic, right? So imagine something like hydrogen chloride, HCl. That is a fairly polar bond, right? Chlorine is the more electronegative of the two, hydrogen not so much. And we know that in the Lewis structure for this compound, there is a pair of bonds, right? So there's a couple of bonds shared between those. If we said to ourselves, look, let's just pretend that this bond is ionic. Frankly, it's pretty close to being ionic, but nonetheless, let's just say that it was ionic and we give all of the electrons of the bond to the more electronegative of the pair, right? So we collect all of those electrons and give them to the chlorine atom. What would happen in that context? Well, what would happen is the hydrogen would then carry a charge of +1 and the chlorine would carry a charge of -1. Those are the oxidation numbers. Those are the oxidation states. And that is how we keep track of, essentially, the electron counts or the electron numbers that each and every atom has throughout the course of a reaction. Okay, so it's a bit superficial, it's a bit schematic, a bit high level. It's not really down into the quantum mechanics of where electrons are spending their time, but it does help us to get a sense of how electrons have moved throughout the course of a reaction. So let's first remind ourselves how to assign oxidation numbers to chemical species. So assigning oxidation numbers or oxidation states comes with a few rules, a few quick rules of thumb that will help you do this for any general chemical species. The first rule is that if your chemical species is an element or it's in its elemental form, the oxidation number is just 0. So a good example of this would be, say, something like molecular oxygen, right? So that's an oxygen atom in its elemental form. Or something like molecular hydrogen, right? Each of the hydrogen atoms in this molecule, each of the oxygen atoms in that molecule is assigned an oxidation number of 0 in that case. Similarly, if you've got other relatively simple chemical systems like monatomic ions, right? So think of something like sodium, the sodium ion, or think of something like chloride, the chlorine anion. Each of these things is a single atom. It has a charge. That charge is, in fact, also the oxidation number. So the oxidation number, of course, of sodium here is, of course, +1. The oxidation number of my chlorine is -1. The third rule is a little more complicated, and it's talking about binary compounds, so things with multiple atoms. How we're going to assign oxidation numbers in that context is the atom that is more electronegative is assigned the more negative oxidation number. And how you can sort of sum this up is that the sum of the oxidation numbers always equals the charge of the particular thing. So for example, think about the molecule PCl3. So in PCl3, chlorine is the more electronegative of these two elements, and so each of the P to Cl bonds we would assume is ionic and give that electron to the chlorine atom, and so each of those chlorine atoms would essentially be a -1, and the phosphorus atom in the middle would have given each of those 3 electrons. It's considered to be +3 at this point. And so this is what I mean when I say that the sum of the oxidation numbers equals the charge. PCl3 as a molecule isn't charged, and so that charge is 0. This is a neutral chemical species. And so the -1 for each of the chlorine atoms must equate to the opposite of +3 of the phosphorus. So the 3 plus each of the -1s equals 0. And that's how we would do this for a lot of chemical species where we might not intuitively know what the oxidation number is. If we can figure out what the oxidation number of its partner is likely to be, we can use Rule 3 to figure that out. So in this case, again, the oxidation number of chlorine is -1, and the oxidation number of my phosphorus is +3. And the fourth and final rule, I suppose, is really just sort of a list of some rules of thumb and sometimes associated anomalies with those. For example, nonmetals are usually negative, and usually the most common nonmetal we're looking for is oxygen. We're looking for the presence of oxygen in a lot of compounds because oxygen is commonly tied to redox processes, not surprisingly given it's sort of baked into the title. Oxygen is generally has an oxidation state of -2, which corresponds pretty well with its position in the periodic table, but occasionally oxygen will be -1 when it's with peroxides. So what are peroxides? Peroxides are compounds that contain an oxygen to oxygen single bond. And so doing Lewis structures will often identify peroxides for us. And they often come with a structure or a formula of O2. Also, hydrogens are usually +1 for, I think, obvious reasons, but there's an exception to that one as well, is that hydrogens can sometimes be -1 when they're bonded with metals. And so we call these metal hydrides. A good example of that might be something like sodium hydride. So NaH, this is a metal hydride, and we can see that the more electropositive element here is written first. So you can see hydrogen over here on the right, which is rare. We don't often see hydrogen written over on that side. And in this particular case, the oxidation number for sodium is +1, and for hydrogen, it's the -1. So have a look for cases like that that are sometimes cropping up in redox processes. And then I suppose finally halogens, typically -1, again for obvious reasons over there on the right-hand side of the periodic table. Halogens usually have a charge of -1. Oxidation numbers are often equal to typical charges, but sometimes halogens will bond with other halogens. And so that's an exception. When you see halogens together, one of them would be positive, one of them would be negative. And so I realize that number 4 is maybe not as concise as we would like, but overall, these are the rules for how we assign oxidation numbers. And assigning oxidation numbers is an important task because if we assign oxidation numbers to all chemical species in a reaction and those oxidation numbers change, there's the key word, if they change for particular elements, we have definitively identified a redox process. So let's quickly look at an example of that. Here's a relatively simple chemical reaction, and our goal here is to determine oxidation states and try to determine if electrons are actually changing hands here. A bit of a simplistic example, but nonetheless, I think it'll serve the purpose. Elements in their elemental form, right? These have oxidation numbers of 0. So the oxidation number for zinc in this particular case is 0. Likewise, for copper, again, these neutral elemental substances, solid metals, for example, have oxidation numbers of 0. And monatomic ions, which I see a couple here as well, they have oxidation numbers equal to their charge. And so we can see that yes, indeed, oxidation numbers have changed throughout the course of this reaction. Zinc used to be 0, is now +2. Likewise, copper was +2 and is now 0. Notice what I mean when reduction and oxidation have to happen together. If you give up electrons, some chemical species must take them, and these are the coupled oxidation and reaction processes that I was mentioning before. So what is reduction? What is oxidation? Well, reduction happens when your oxidation number gets reduced, right? So this is a reduction in oxidation number, and my 2 got reduced down to a 0. Likewise, oxidation is the opposite, right? So it's the conjugate pair, if you will, to the reduction process. Every reduction comes with an oxidation, and again, oxidation is when we increase our oxidation number. And so we can see that zinc has been oxidized, copper 2+ has been reduced, and likewise we could say that the copper 2+ was the oxidizing agent that helped me oxidize the zinc. Likewise, the zinc was the reducing agent that helped me reduce the copper. So that's the terminology we use in this particular application. You may have heard of some mnemonic devices such as Oil Rig or Leo the Lion says grr. These are to help us remember this sort of ordering of terms in a redox process, right? Oxidation is loss of electrons. Notice that my zinc lost electrons to become positively charged, and that is, of course, the oxidation in this particular reaction. Notice also reduction is gain of electrons. Clearly my copper 2+ ion had gained electrons to ultimately become neutral. Likewise, Leo, so loss of electrons is oxidation, gain of electrons is reduction, same sort of deal. And this is sort of how we describe this process. But whether or not this process will even happen in the first place is related to something called the activity series. The activity series is shown here, which is really just a listing of all of these elements, mostly metals, and their oxidation reactions, which is, of course, removing an electron from them. And this list is presented in the order of ease of oxidation. So the ease of oxidation increases at the top of the list. So lithium, very easily oxidized. Gold, however, not so much. And that should make sense. Look at what's on the bottom of this list. Things like gold and platinum and silver, high-value metals. Wouldn't be so good if these metals were very easily oxidized. In fact, they wouldn't be as precious as they are if that was the case. So what this activity series allows us to do is evaluate whether or not a particular redox process is likely to happen. For example, referring back to what we have here, this is a process by which zinc is oxidized by copper. So can zinc be oxidized by copper? That question is answered by where they are relative to one another in the activity series. Notice that zinc is right here, above copper, which is right down here. That tells me that zinc is the more easily oxidized of those two metals. And so if we had a choice of copper oxidizing zinc or zinc oxidizing copper, the winner of that choice is actually how it's written right here. Zinc is the more easy of those two elements to be oxidized, and so the activity series helps us describe this and helps us understand why this particular redox reaction, first of all, that it is, but second of all, that it will proceed precisely as we've written and not in reverse. This is useful if we're thinking about batteries. Batteries are one of the most obvious applications of redox processes. If we want electrons to transfer, what if we were able to harness those electrons, put them through a wire so that they can drive an electrical device? That's precisely what is going on inside a battery. And this is our zinc-copper reaction phrased in the term of a battery. So let's have a look at how this works. We've got an oxidation reaction happening in our beaker to the left, and the reduction reaction happening in the beaker on a right. We can literally split these reactions among two different beakers beakers, right? So here's our oxidation reaction where our zinc is going to gain electrons, and here's our reduction reaction where our zinc was going to give up electrons and our copper is going to take them. So how can we actually cause that to happen? Well, what we need to do is supply what's known as a salt bridge. So this salt bridge provides the necessary ions that will allow the electron transfer to happen, right? Zinc essentially wants to give up its electrons. Copper wants to collect them. And so that will happen through this wire that we've connected across those two different pieces of metal. Zinc being referred to as the anode, where oxidation happens, and copper being referred to as the cathode, where reduction happens. But in order for that electron transfer to happen, obviously we are going to have a buildup of electrons over here and a decrease of electrons over here. So what will happen to counteract that process is that our zinc ions will go into solution and be balanced, if you will, charged balanced by the salt bridge. So the salt bridge provides enough ions of the appropriate charge to keep both beakers charge balanced. And those electrons are then allowed to flow. Over time, you'll see what happens is the zinc anode eventually erodes, and the copper cathode eventually builds up, because all of the copper ions that were in solution will now jump onto the piece of metal to collect those 2 electrons that are gathered there in order to turn into solid copper. So this is precisely how a battery works. We use the activity series to determine which metals can be paired such that one likes to be oxidized and one likes to be reduced, and that will cause significant voltage to be passed through this system, which we can harness to do work and send text messages, I guess. All right, but now we need to balance these redox processes. We need to take these equations and balance them in terms of atom types, making sure that there's the equivalent number of every type of atom on either side of the equation, as well as in terms of charge. We need to make sure our charge is equivalent on both sides of these equations. Now, why do we tend to focus on balancing redox processes? Why is that a special thing? It's a special thing because it's notoriously difficult to do. These special types of reactions, these redox reactions where electrons are changing hands, are often tricky to balance for a whole host of reasons. But what I'm going to do right now is show you a relatively accessible way of balancing redox processes called the method of half reactions. Okay, so what we're going to do is we're going to learn how to do this method of half reactions, and it's in a series of steps. And one of the first things that we need to understand is that when redox processes are balanced, we often assume that the reaction is occurring in an acidic or basic medium, right? So there's either excess protons, if this is in an acidic medium, or there are excess hydroxide ions, OH-, if it's a basic solution. And the reason we assume this is because it's generally true, and that assumption will allow us to essentially play some tricks to help us balance it that much easier. Now, what many textbooks will do will show you different methods, different techniques for balancing redox processes in each of these different types of environments, one for acidic, one for basic. What I'm going to do is I'm going to show you one strategy that'll work for both. We're going to balance these equations assuming an acidic medium, and then if we happen to have a basic medium, which is generally told to us in the question, we can adjust at the end. So there's a final step that's an optional step that'll take us from the final solution in acid and convert that to the final solution in base, which will work for us the vast majority of times, if not every time that we'll ever see in this class. So here's an example. We've got MnO4-, so the permanganate ion, reacting with C2O4 2-, and we're going to get some Mn2+, some manganese ions out on the other side, some carbon dioxide. So this is not balanced, and what we're going to do right now is balance it using the method of half reactions. Now, in the method of half reactions, what we're interested in doing is splitting this reaction up into the reduction half and the oxidation half. Now I've just gone on and put some oxidation states onto each of my atoms in this process so that it's fairly clear to me which element undergoes which process. For example, manganese goes from a +7 oxidation state to a +2, so it's clearly been reduced. Likewise, my carbon atom goes from a +3 to a +4, and so it gets oxidized. And these are each of my half reactions. All right, now that I've got my reaction split into its two halves, the reduction half and the oxidation half, I have to follow a very specific series of steps to balance this. The first step, after splitting it into its half reactions, is to balance all of the elements that aren't oxygen or hydrogen. So we're going to leave oxygen and hydrogen till the very end, and right now what we're going to do is balance all of the other atoms. In my first reaction, I can see that I've got a single manganese atom on both sides of the equation, so it's already balanced. Whereas in my second, in my oxidation reaction, I can see that I've got two carbon atoms on the left, but only one on the right. So the way to fix that is to, of course, add a coefficient of 2, and now my carbon atoms are balanced. The next step is to balance oxygen atoms, and how we balance oxygen atoms is by using water. These are all aqueous species, so they're all existing in water. Even if they weren't, so long as some are, we know that this is a solution that's surrounded by water. So water is able to be used as a reagent whenever we need it in these processes. And in the first reduction reaction, we can see that we've got 4 oxygen atoms on the left, and we've got none on the right. So the remedy is to add enough water molecules to give me 4 oxygens, which is, of course, 4 water molecules. Now, in the second reaction, I can see that I've got 4 oxygen atoms on the left, and I can see that I've got 2 oxygen atoms for each carbon dioxide molecule, but of course I've got 2 carbon dioxides. So my oxygens are balanced in this oxidation reaction. Now, you can see at this point why I've left hydrogen until the very end, and that's because had I balanced hydrogen before this point, adding water would have thrown off my count of hydrogens, so it's really best to leave this to the very end. Now, in the reduction reaction, I can see that I've got 8 hydrogen atoms. And so what I'm going to need to do is add 8 hydrogen atoms to the left-hand side of this equation. And how I do that is in the form of H+ ions. You'll recall I assumed that this process was happening in an acidic medium. You'll learn all about acids and bases next semester and their properties and how to predict those properties and pH and all that stuff. But for now, essentially I'll remind you that the signature of an acidic solution is an excess of H+ ions floating around in that solution. So if this is in fact an acidic solution, we certainly would have H+ ions available to us to use in this reaction. Now, in my subsequent reaction down here, this oxidation process, I have no hydrogen atoms on either side of the reaction, so it's already balanced. Now, the final thing that I need to do to each of these half reactions is balance them according to charge. So charge is important. If I don't have equivalent charges on either sides of these reactions, I don't have the appropriate numbers of particles, specifically electrons. Notice on the left I have 8+ associated with the protons. I've got a minus associated with the permanganate, and so this has a total charge of +7 on the left-hand side of the reduction reaction. On the right-hand side of the reduction reaction, I have a total of +2. So this one is not quite as high. The +7 is larger than +2. And since electrons are negatively charged, I need to add them to the side of the reaction that has a charge that's too high. In other words, I need to add them to the left of the reduction reaction. So I've added 5 electrons to the left-hand side of the reduction reaction. In the oxidation reaction, I see that my left-hand side has a charge of 2- and my right-hand side is neutral. So again, I look for the side of the reaction that's too high, and that is, in this case, the product side. And that should always be true. When balancing your half reactions, you will add electrons to the opposite side of each of the halves. So the right-hand side or product side of my oxidation reaction is now too high by 2 charge units. It's neutral, whereas the left-hand side is -2. So what I need to do to balance this is add 2 electrons to the right-hand side of my oxidation reaction. And now each of my halves is balanced in and of itself. The final step is now placing these 2 reactions together. We'd like to add them both, and just like when working with Hess's law, adding 2 reactions is a relatively simple process. We simply sum up all of the things on the left of both reactions and all of the things on the right of both reactions. The problem in this case, though, is with the electrons. Notice there's 2 electrons in the oxidation reaction, but 5 electrons in the reduction reaction. Therefore, they won't cancel. There'll be leftover electrons in this reaction, and that's a very odd thing to have written in a chemical equation. We're using and explicitly writing out these electrons in the half reactions because we have to when the equation is split into halves, but also because we want to be very clear about the amount of electrons that are changing hands. In the first reaction, it's 5, but in the second reaction is 2. So it won't be balanced when we put them together. They're balanced individually, but not together. So what we need to do is multiply one or both of these equations by the appropriate coefficients to allow the electrons to balance. A 2 and a 5 really requires that we multiply each by each other. So for example, this first reaction will need to be multiplied by 2 to give me a total of 10 electrons, where the second reaction will need to be multiplied by 5 to give me, again, 10 electrons. So let's do that now. We'll start with our electrons on the reduction reaction, which will become 10. My 8 hydrogen atoms will become 16, and the rest will be as follows. Now, moving on to my second reaction, recalling that I'm multiplying it by 5, I get the following result. And now I have a situation where I have the same numbers of electrons on either side of the reaction. These can now be summed together. So I will sum all of the species on the left-hand side, and I will sum all of the species on the right-hand side. And there you have it. That's my final answer, my final balanced redox reaction, again, assuming acidic conditions. And so you can see that it's quite an involved process and not a trivial exercise to balance these different chemical entities, these redox processes. But that's how it's done. We start off by splitting into halves, then we balance elements that are not oxygen and hydrogen. We balance oxygen with water. We balance hydrogen with H+, and then we balance charge with electrons. The final step is making sure that each of our electron numbers are the same so that when we add the 2 half reactions back together, we have no electrons remaining. The intention is that they'll cancel on both sides, and we're left with the final balanced reaction. Now, what would we do if our task was to balance this chemical reaction in a basic solution? Well, we can follow all of those same steps and simply fix it at the end. Fix what, you might ask? Well, this 16H+, as I said before, is indicative of an acidic solution, which I now don't have. If this is a basic solution, this is an unrealistic species to have in my chemical process. So let's copy this reaction, and I'll show you the subtle change we need to make to balance this in base. So here is our final result from a balancing in acid, again highlighting the fact that my H+ is my culprit in this particular case. It's the one that is indicative of an acidic solution, not a basic solution. How do we deal with that? Well, recall what is indicative of a basic solution, and that is in fact OH-. So what we need to do is replace the H+ with OH-. Now, how are we going to do that? Well, if we add H+ and OH- together, they just form a water molecule. So really the key here is to add as many OH pluses to this reaction as we had OH minuses as we had H pluses in the first place. Now, to prevent us from throwing this equation out of balance, we will need to add that much OH minus, in fact, to both sides of the equation. On the left-hand side, in this particular case, what will happen is the H plus and the OH minus can come together to create 16 water molecules. And left over will, of course, be the 16 OH minus that I added to the right-hand side. So there you go. And essentially, I'm finished at this point, except I can notice that there's just a bit of redundancy given the fact that there's 8 water molecules now on the product side and 16 on the reactant side. We can be a little bit more efficient here by canceling the 8 that are on the right with 8 of the total of 16 that are on the left. And this will give me my final balanced equation in basic solution. We can see that I've got 8 water molecules, 2 MnO4 minus, 5 C2O4 2 minus, reacts to produce 2 manganese cations and 10 carbon dioxides with 16 hydroxide anions. And this is my balanced equation in base, where the final step was simply to add as much OH minus to both sides of this reaction as the number of H plus that I had in solution. And so that converted that H plus to water, and really all I did was get rid of any redundant waters on both sides of the equation. And so there you have it. That is balancing redox processes, both in acidic media and in basic media. So back to the rust problem. How does it get there, and how can we prevent it? Well, as you can see, iron is oxidized by oxygen. In the presence of water, and a little acid doesn't hurt either. So all that salty slush on the roads in the wintertime comes with all of the above. And it isn't any wonder that cars don't last long in the Canadian climate. But it doesn't mean there isn't anything we can do about it. Providing waterproof barriers is a good solution, like undercoating. Oil products are used to coat the metal surfaces, and because oil is a non-polar molecule, it doesn't significantly interact with water, and therefore water doesn't penetrate. You could also use a sacrificial metal. Zinc, for example, is commonly used to coat metals that are said to be galvanized. The special property that zinc has is simply that it's cheap and more easily oxidized than iron, so the iron is protected. Either way, though, it's all chemistry.